Hey everybody. So today we're recording the first lecture in a different place. We are now in Soda. We're likely going to be here for the next few weeks because we do not have access to Dwinell. So this is going to be the new format. So today we're going to continue discussing computational problems that are related to linear programs. You have seen two lectures on linear programming, so what it is and how to formulate linear programs, how to take their duals, the notion of weak duality, strong duality. And you've also, at this point, had two lectures on network flows, which is a particular case of sort of linear and really actually also integer programming. Today we're going to look at another very interesting problem that is also a special case of linear programming, and it's related to game theory. So today we're going to study zero-sum games. We only have one lecture about zero-sum games, so the goal for today is going to be to define what they are. We're going to go through some examples and then connect them back to the notion of linear programming. So let's get started. So today we're going to talk about zero-sum games. And before I give an abstract definition, I want to motivate studying this notion via an example. Okay, so we're going to first move these chairs. Okay, look at the example of rock, paper, scissors. Okay, so this is a familiar game. You play at the same time with somebody else, and we can abstractly represent this game via a so-called payoff matrix. Okay, so this payoff matrix is going to have 3 rows and 3 columns. Now, the rows are going to represent the options for one of the 2 players, which we're going to call the row player, because we're associating them to the rows. Now, because this person is playing in rock, paper, scissors, they have 3 options they can play, either rock, paper, or scissors. Okay? So we have 1 row represent each of their actions. Then we have the column player. And in this game, because this game is symmetric, they too have 3 actions they can take in this game. They come to the same names: rock, paper, scissors. All right, so 3 rows and 3 columns. Now we have 9 cells. These are the 9 outcomes of the game rock, paper, scissors. And now we want to model the outcomes, these 9 outcomes. So as you may recall, when in this game, when you play the same sort of strategy, say both players play rock, so that would be this cell over here, then that is a tie. So we're going to denote that with a number in this cell, let's say 0. Now, what does 0 mean? This means that the utility of either player is 0. In both cases, neither of them won or lost any units, sort of say they were betting money, any dollars, or any units of happiness. Okay? So that's what happens on the diagonal. And now let's look at, for example, in the case where the row player plays paper and the column player plays rock. In this case, the game dictates that the person playing paper and the row player wins. So how do we denote in this game that this person wins? Well, we're going to take always in zero-sum games the perspective of the row player, and we're going to put, let's say, a 1 here. Now, this 1 here signifies that row wins 1 and column loses 1. So we're taking the perspective of the row player. Okay? So by symmetry, when the column player plays paper and the column player plays row, here, because we're taking the perspective of the row player, we're going to put here a minus 1, okay? Because this would be saying that row wins -1, which means it loses 1, and column wins, so loses -1, which means that he wins 1. Okay? So we can similarly fill in this table and say, for example, when the row player plays scissors, and you have rock. In this case, the column player wins. So we have a -1 here. By symmetry, we have a 1 here. And when the row player plays scissors and the column player plays paper, then he would win. So we have a 1 here, and by symmetry, a -1 here. Okay? So this is the payoff matrix of rock, paper, scissors. Okay? And once again, all of these are from the perspective of the row player. Okay? Now, this is a game, and in this game, both of the players want to try to win. So at a very high level, we should remember that the row player wants to maximize kind of the value of the cell, okay, whatever value of the outcome he's in, and the column player wants to minimize the value of the cell that he ends up ending up into. Okay? The reason why these games are called zero-sum is because we have this condition that every unit that the row player wins, it's a loss to the other player. So implicitly, what we're actually not writing is that in each cell we could have written the kind of the winnings of both players. So here we're kind of imagining that, but we're not writing that there is a pair here, 0, 0, where 0 for the row player and 0 for the column player, 0, 0, 0, 0. And in this case, we would have 1 and -1, -1 and 1, right? 1 and -1. And in all of these cases, because every unit of winning is a unit of losing for the other player, the sum of the two entries is 0. That is why this is called a zero-sum game. But because we know that the sum of the entries is 0, we don't bother writing the second entry, and we just take the perspective of the row player. Now, we're in a class about algorithms. Why do we care about algorithms and zero-sum games? Well, specifically, we are interested in solving a game. What does solving a game mean? It means to derive a strategy that is good or, say, optimal for either of the players. So to gain some intuition about what that would mean, let's sort of go through some examples of strategies playing in this game and see sort of how much either player is winning. And with this intuition, we'll see what does it mean to have a solution. The first point that I want to make, though, is that I want to make a distinction between pure strategies and mixed strategies. So what does it mean for a player to play in the game? Now, what you should think about is that, sure, there is the player. Like in front of him, he has several buttons. There are 3 buttons corresponding to rock, paper, and scissors. And he gets to choose which one to pick, to press and play. But notice that these are just kind of what are called the so-called pure strategies. He could say, well, today I'm going to play rock or paper or scissors. But in reality, his kind of strategic space of possibilities, like the types of strategies he could play, is much bigger than that. He could, in fact, for example, assign a probabilities distribution across the pure strategies. So we also have the notion of a mixed strategy, which is a distribution on pure strategies. For example, he could say, today I'm going to play with probability 5 1 over 5 rock, then probability with 2 over 5 paper, and with probability 2 over 5 scissors. That would be an example of a mixed strategy over the pure strategies rock, paper, and scissors. So essentially, now what we're asking is, we should be asking ourselves which mixed strategies are good strategies to play in this game. So in general, just to have some notation, we're going to say that rho plays some vector x, which is x1, x2, x3. These are probabilities x1, x2, and x3, to mean that he's playing x1 rock plus x1 paper plus x1 scissors. And we're going to represent this mixed strategy by just a vector. And column, he's going to play a strategy y, again, which represents the corresponding, wait, I don't know whether it's x1, x1 here, x2, x3. x2 paper plus y3 scissors. Okay? Now, when this happens, the outcome of the game is a random variable. Notice that if players play mixed strategies, the outcome is a random variable. This means that the player should care about some properties of this random variable. For example, the row player wants to find outcomes that have high value, and the column player wants to find outcomes that are of low value. But this is just a distribution. So typically, what people do, they're going to look at the expected value of the outcome. Okay, this is called the expected utility. So it's the expectation of the utility. And it's just the sum over all I and j of outcome I and j. So that this denotes the cell inside here, xi, yj. Why xi, yj? Because this is a probability that when the two players play, the row player plays outcome I with probability x, and the column player will choose strategy j with probability yj. Okay, in this case, we have rock I equals 1, paper is I equals 2, and scissors is I equals 3. Okay? All right, so now we're going to look at some examples of mixed strategies to see how this notation plays about. So, as probably some of you already know, in rock, paper, scissors, it is usually not a bad strategy to play at random. So let's see how the random strategy fares using this notation. So let's look at examples of mixed strategies. So let's say that row plays at random, which means that he plays x equals to a third, a third, a third. And let's say the column stubbornly plays scissors. Okay? Again, this is a mixed strategy that assigns equal probability to all of the options. And this is a pure strategy that puts all the probability mass on scissors. If this happens, then the expected payoff for the row player, again, because we always have the perspective of the row player, is what? Well, we have this sum to compute. But really, if you go back here, because we know that the column player will only going to play scissors, the expected outcome is going to be a third of the time 1, a third of the time -1, and a third of the time 0. Okay? So we basically play, the expected outcome is the average of these values. So we can write it as follows. We have outcome 1 with probability a third times 1, plus outcome -1 with probability a third times 1, plus outcome 0 with probability a third times 1. And that would be 0. So the expected payoff is 0 because this term is 0 and these two terms cancel one another. So this is saying that if rho plays X, which is a mixed strategy that is fully random, then the expected outcome is 0. So that was the first example. Let's try to do something slightly more complicated. Let's say that rho player plays X, which is again at random, but the column player plays some generic strategy y1, y2, y3. Okay, so we're just kind of trying to do a similar computation where the row player still plays at random, but the column player plays a y that is generic. Okay, in particular, it could, for example, be the pure strategy on scissors, but it could be something else. Let's try to look at the expected payoff again. And so at the end of this computation, something interesting will come out. So we need to compute this value, right? So let me rewrite it here. Sum over ij, uij, xi, yj. Now notice that xi is always a third, so I can rewrite this sum of 9 terms by first summing over j, then putting a third here. We have sum over I, then u, ij, and then yj. So basically I'm just saying, look, all of the xi are the same. Those are the third. And I'm just bunching together all of the values over I. But notice that this is just saying, consider the average of column j, because I'm summing over I, and then dividing by 3. But for any column j, whether it is this column, or this column, the average is always 0. So this means that I'm summing 0 times yj, which is 0. Now, what have we learned is that the strategy of playing at random has the property that not only when the column player plays scissors, it has expected payoff 0, but moreover, when the other player plays some strategy, really any strategy, the expected payoff is still 0. Now, because this game is symmetric, it could be that the column player also plays at random, which means that no matter what the row player does, the expected outcome is again 0. So we learned something, that in the game of rock, paper, scissors, rho has a special strategy, x star, the random one, that ensures that the expected payoff is at least 0. And column has a strategy y star, in fact it's the same strategy, that ensures that the expected payoff is at most 0, because he wants to minimize. This also means that x star and y star are the best strategies that either player could use, because the row player cannot expect to find a strategy better than X star that always ensures that expected payoff is more than 0, because the column player does have a strategy that makes sure that the expected payoff is no more than 0. So this means that we say that the value of the game is 0. There is this kind of equilibrium where the best strategy of one player ensures that the same expected outcome as ensured by the best strategy of the other player. In particular, either player knows in advance that the other player will play their best strategy, okay? And there is no hurt. It doesn't hurt to know that. So this is what we would like to do today, is we want to understand for zero-sum games how to find these X star and Y strategies that make each player kind of force the hand of the other player, and so that the other player has no better strategy to use. So that it is what we want to do today. Now, rock, paper, scissors is a little bit degenerate as a game because it is symmetric. Both players kind of have the same type of strategies. And because they're the same type of strategies and symmetric payoffs, then it turns out that the best strategy for either player is this kind of boring random strategy of just a third, a third, and a third. So what I want to do right now is I want to look again at an example, just a non-symmetric example. And we're going to see in this non-symmetric example how how there is still a best strategy for either player, but it is not the random one, and there are also different strategies depending upon whether you're the row or the column player. After this example, we'll talk about how this relates to linear programming. All right, so talked about rock, paper, scissors. Let's talk about example number 2, something non-symmetric. So here it is. So we're going to, for simplicity, look at a game with just two strategies for either player. For the row player, we have top and bottom. And for the column player, we have left and right. And the values are going to be 5, -3, and -1 and 1. Okay? So this fully specifies the game. And first, kind of the first remark that we should make is that playing at random is not an interesting strategy, okay? Let me maybe make this point over here. So remark, kind of playing at random is not an interesting strategy. I will say what interesting means in a moment. Just want to, look, you can really feel that playing at random was a good strategy just in a particular game, but not in every game. So if row plays, say, this strategy, which means with half probability plays top and half probability plays bottom, then the column player has a choice, right? He could play either left or right. Now, the column player is strategically thinking which of these options he might play if he believes that the row player is going to play at random. So let's see, like, what should he do? Playing left means that half the time he will have payoff 5, and half the time he will have payoff -1. So it means that expected payoff by playing left against this strategy would be 5 over 2 minus 1 over 2. That would be 4 over 2, that is 2. If he plays right, it means that half the time he will have payoff minus 3, and half the time he will have payoff 1. So that would be minus 3 over 2 plus 1 over 2, and that would be minus 1. Now, between these two, for the column player, it is better to play right because he wants small payoffs. Remember, because the payoffs are for the row player, and so the column player wants to reduce those. So if row were to play this strategy, the column player would always play right as a pure strategy because it's just strictly better than this one. Kind of similarly, if the column player plays a y equals a half and a half, then the row player has two options. He could either play top or bottom, right? If he plays top, half the time he will have payoff 5, and half the time he will have payoff minus 3. So that would be 5 over 2 minus 3 over 2. So that would be 1. If he were to play bottom, half the time he would have payoff minus 1, half the time 1. So that would be minus 1 over 2 plus 1 over 2, so that's 0. Because the row player wants to maximize the payoff rather than minimize it, he's going to select always top. Now, what we see here is something that is very different than what we saw in the case of rock, paper, scissors. We see that if row were to play at random, then the column player would be able to force the outcome of the game to be minus 1. The value of the game to be minus 1. Whereas if the column were to play at random, then the row player would be able to force the value of the game to be 1. Notice first and foremost that these are different values, and these themselves are different values. Okay? So it seems like either player probably has a better strategy because these two values do not match. Okay? There is no reason to believe that there isn't a better strategy that row could play that would guarantee an outcome that is above minus 1, nor does column have any reason to believe that there isn't a better strategy than this one that would guarantee an outcome that is smaller than 1. Okay? And indeed, now I will exhibit two different strategies that have these properties, they will force the value to be between minus 1 and 1. So for now, I am going to sort of propose two strategies. For now, they're unmotivated. We don't know yet where they come from. The point is to come up with an algorithm that derives these strategies. But now we're going to first see how these other strategies that are not random behave. So consider the following strategies. So if row plays x, which is a fifth and 4/5, okay? No, this is not a random strategy. It's just a different strategy. Again, I'm not saying yet where this strategy comes from. We want to compute this strategy later. Then the column player has two options, either left or right. Now, which one should he do? Well, if he plays left, he will see 5 a fifth of the time and minus 1 4/5 of the time. So that means that here it's 5 over 5 minus 4 over 5. So that's 1 over 5. If he plays right, that means that he sees minus 3 a fifth of the time and 1 4/5 of the time. So that would be minus 3/5 plus 4/5, that is 1 over 5. Which one is he going to pick? Well, he doesn't really care, because whether left or right, either of them gives him a fifth value, so it doesn't really matter for him. Now, if the column player plays a strategy Y, which I'm, again, writing down and I'm not explaining where it comes from yet, 2/5 and 3/5, then the row player has two options, either top or bottom. If he plays top, he will have 5 2/5 of the time and -3 3/5 of the time. So that would be 5 times 2/5 -3 times 3/5. Okay? So that is 10/5 minus 9/5, so that is 1/5. And if he chooses bottom, he will see -1 2/5 of the time and 1 3/5 of the time. So that's -1 times 2/5 plus 1 times 3/5, and that is 1/5. And again, he doesn't care which of these two. So now notice that something similar as we've seen before happens. If either player plays this magical strategy, then they are able to force the same value for the outcome of the game. Okay? So the row player has a strategy that ensures that the outcome of the game is at least a fifth. And the column player has a strategy that ensures the outcome of the game is no more than a fifth. So it means that either player has no better strategy. So it means that X and Y is a solution to the game. Okay? So the question that we want to ask today is, maybe let me put it here, given the payoff matrix Uij, how do we find the optimal strategies X star and Y star for row and column respectively? We want to somehow mechanize finding this X star and Y star. So we're going to now connect this type of reasoning to linear programming. So what I want to do next is I want to try to abstract away the reasoning that leads to these choices of 1/5, 4/5, and 2/5, and 3/5. We're first going to do it in the special case of this game. And then I'm going to sort of point out how essentially that's what can do for any game. So I'm going to do that here. And give myself a little bit extra space. Okay, so finding X star and Y star for this game, that game. Well, I guess the arrow should go the other way. So in general, row player can reason as follows. Say I'm the row player, and I'm playing some strategy X, which is X1 and X2. I don't know yet what is a smart value of X1 and X2. But I definitely know that if the column player believes that this is what I'm playing, then the column player will reason in a similar way as before. He will say, well, I could play left or I could play right. Now, if he plays left, he knows that the expected outcome is going to be 5 times x1 minus 1 times x2. And if he plays right, his expected outcome is going to be minus 3 times x1 plus 1 times x2. And what he's going to pick, the smaller of the two. Right? So for example here, of the two, he picked this one because it was minus 1. Over here, because x star was chosen appropriately, actually it didn't matter to him whether left or right. But now we're going to try to kind of view this reasoning as a linear program. It seems surprising that we can, take this reasoning here and turn it into a linear program. Okay, so that is what we're going to do right now. So first, we want to say that we can rephrase this reasoning over here to be as follows. We want x, which is x1, x2, that maximizes the minimum of these two options, 5x1 minus x2 and minus 3x1 plus x2. Why? Because if he plays x1 and x2, he knows the column can either pick left or right, and he's going to pick the one that minimizes the two. So given that column is going to minimize, given that row is going to experience the minimum of this and that, he wants to pick x1 and x2 to maximize the minimum of this and that. Okay? So this rephrasing over here, now we're going to write it as a linear program. And the only thing, so we're really almost there. The one thing that is not clear is that we have this minimum here, which doesn't feel like a linear anything, right? Linear programs, you want a linear objective function, linear constraints. What is this thing? Like, how can we handle minimum within a linear program? Well, here we're going to use a little trick, some sort of gadget that implements minimum using linear constraints. So we're going to have an auxiliary variable, max z. So z is going to be an auxiliary variable such that z is at most the first term, 5x1 minus x2. Z is at most the second term, minus 3x1 plus x2. And then we're going to constrain x1 and x2 to be a probability distribution. So we're going to say x1 plus x2 is 1, and x1 plus x2 is non-negative. But let's focus on this part here. So we're maximizing a particular objective function, z. By the way, the variables are z, x1, and x2. So the objective function, you really should think about it, is z plus 0 times x1 plus 0 times x2. It's just that x1 and x2 do not participate in the objective function that we're maximizing. So if you maximize z, subject to these constraints, notice that if you're ever in a situation where z hasn't met yet both of the upper bounds, this one and that one, like both of these are strict, then we're clearly not at optimum because we definitely can increase z a little bit. So we will only be at optimum only when z matches one of these, and that would be the minimum. Okay? So kind of this mini gadget over here with this maximization function is implementing for us the minimum here. And here is the linear program that if we solve is going to give us x star, which is x1 star and x2 star. So we took the generic reasoning of the rho player and said, I'm just going to pick the best thing possible subject to these constraints. If I play this, I'm going to experience the minimum of these two options, and I just want to maximize that. Okay? So I'm going to do this again for the column player, and then we're going to see that the column player's reasoning is actually the dual, okay, of the rho player. So let's do that here. So if column plays y, which is now generic y1, y2, then the rho player has a top and a bottom option. So in the top option, he is going to experience 5 with probability y1 and -3 with probability y2. So here I'm going to write 5 times y1 minus 3 times y2. And if the rho player plays bottom, he's going to experience -1 with probability y1 and 1 with probability y2. And he will pick the bigger of the two, because the rho player wants to maximize the payoff. So we're going to view this reasoning as a linear program also. And again, we can rephrase this as we want y, which is a tuple of y1, y2, that now this time is going to be minimizes the maximum of the two options, 5y1 minus 3y2 and minus y1 plus y2. Okay? Because, again, why? Because the column player is considering some strategy y. If the rho player knows that the column player will play y, then he is going to pick the maximum of these two things. So the column player better pick y to minimize the maximum of these two things. That's why we wrote this. And now, just like before, we have an optimization problem, except that now we want to minimize instead of maximizing. And our objective function doesn't look linear, right? It's this thing here. But we can use an analogous trick as the one that we used here to kind of make the maximum go away. So we're going to say that we're going to minimize w such that w is at least 5y1 minus 3y2, and w is at least minus y1 plus y2. And then we also have to ensure that y1 and y2 are a probability distribution by saying y1 plus y2 is 1, and y1 comma y2 is going to equal to 0. Okay? So this is the linear program that represents the reasoning for the column player. Now, and again, like before, in the objective function, we also have implicitly, though they do not participate, the variables y1 and y2, they just have 0 coefficient in front of them. So the variables are 3 variables, w, y1, and y2, with these constraints. Now, if we compare this linear program and this linear program, we will see that the coefficient matrices are transposes of one another. Here we have a coefficient matrix, which is 5 minus 3 minus 1 and 1. And here the coefficient matrix is 5 minus 1 minus 3 and 1. They're transposes of one another, and with some massaging you can see that these two programs are duals of one another. When you take the dual of a linear program, you have to transpose the matrix and you have to do a couple of other things. But this is telling us that looking for the best strategy for the row player, it is this linear program. Looking for the best strategy for the column player, it is this program. And because these are dual of one another, strong duality tells us that the maximum value of this program equals the minimum value of this program. It turns out it is the value of the game, and that is precisely why, in this case, X star achieved the value of the game at 1 over 5, Y star achieved the value of the game 1 over 5, and these values are the same. Because the strategic reasoning of one player is the dual of the other, and so there is a solution which is the maximum and minimum respectively of each of their optimization problems. So now that we've seen this, in fact, several times, we've seen reasoning for rock, paper, scissors with a random strategy. We've seen what happens with a non-random strategy, with a random strategy in I also wanted to remark, notice that this 1 over 5 is between these two, right? In this interval from -1 and 1, it contains 1 over 5. Why? Because this strategy is better for the row player because it achieves a larger value. And this strategy is better than this one for the column player because it achieves a smaller value. That's where they meet in the middle. Okay? All right. So now that we've seen how to work with concrete examples, in particular, we went several times for this non-symmetric game, first with random strategies, then the solution, and then we abstracted away the solution as a linear program, still for this game. I want to talk about what is the general paradigm for any zero-sum game. So I'm going to do it here. All right, so a game now is specified by the payoff matrix U. So you have some number m of rows and some number j of columns. Okay? So in general, it doesn't have to be the same. We've seen a 3x3 game, a 2x2 game. Now we have an m by n game. So you have this matrix, has numbers inside. There's m rows and n columns. And what we want to do is we want to find the solution, x star and y star, for this game. So a row strategy is a vector x, x1 through xm, right? That is a probability distribution. So you're going to have x1 all the way up to xm is 1, and all of these things are non-zero. And a column strategy is a vector y, y1 through yn, where again, this is a probability distribution. So y1 plus up to yn is 1, and all of the yi's are non-negative. And kind of the expected payoff is sum for I in M, so j in N, uij, xi, yj. Okay, so this is kind of a general setup. So now I want to find x star and y star in this like quite general setup. Oh, I forgot to mention. So one may wonder, why on earth are we looking at expected payoff? Why specifically would the players be interested in maximizing or minimizing the expected payoff, respectively? This is a good question. Nobody asked it, but I'll bring it up anyways. And it's really like a modeling. It's a modeling assumption. Okay, so this is basically saying that a player cares equally the same way whether they, say, with probability 1 have payoff 0, or with probability half payoff 1,000 and probability half payoff minus 1,000. In expectation, they are the same, so they care the same way about either outcomes, about either possibilities. Often in game theory, people assume that players are so-called expected utility maximizers. This is also known as risk-neutral players because all they care about is expectation. More generally, in game theory, it doesn't mean that people model strategic behavior always in this way. It's just one of the ways in which people model it. If you look at zero-sum games under a different notion of strategic behavior, then you're going to get sort of different type of analysis and different structure. But so looking at expected utility is kind of part of the description of the problem. It doesn't mean that when you as a person go and play in a zero-sum game, this is definitely what you're going to care about. It is just kind of a modeling choice. All right. So this is the general payout, the general setup. And what we want to compute the solution of the game, x star, y star, okay? And if one were to just give you this generic formulation, it would be wildly unclear what to do. But fortunately, we have gone through many examples, and now we have uncovered the linear programming structure of this problem. And now I will show how it's actually fairly straightforward to write a linear program for the row player and the column player, respectively, that you can go ahead and just solve using any of the algorithms for linear programming. In particular, you can plug into an LP solver, and it will give you the answer rather efficiently. So if the row player plays, now we're again trying to model a generic strategy, x1 through xm, okay? Then column will pick some y to minimize the expected. I'm going to write it this way. I'm going to I want to define here a notation that I'm going to keep using. I'm going to write u of x, y. X and y are probability distributions. Is this expectation? Okay? So I'm just using this notation, u of x, y. These are not I and j. These are probabilities. Okay? Maybe I'm going to denote it this way. Expected utility of x and y. To minimize expected utility of x, y. Okay, so that's exactly what the column player should do. It should pick y to minimize this expectation. It's exactly what it was doing here. So, all right. So the payoff for rho is minimum over y of expected utility of x and y. But really, let's open up this one for a moment. This is a sum for j equals 1 to n of expected utility of xj times yj, right? Because y with probability yj is just j, okay? So there's a minimum that I need to put here. Sorry. Minimum y sum from j equals 1 to n expected utility of xj yj, right? So what I've done from here to here, I've just opened this expression up in one of the summations. But look at this. I have a convex combination of n numbers, like this thing, right? I have when j equals 1, when j equals 2, these are all numbers. Now I want to pick y such that it minimizes this sum. Now y is just a probability distribution. So think about it. I have different numbers of different sizes, and now I need to assign a probability so that when I take a random one, I minimize kind of the expectation. What I should do is I should put probability 1 on the smallest one. So this thing is the same as the minimum over j of expected utility xj. There's no, like, one of these numbers will be smallest, okay? It is better for me to put all the probability mass on that one, okay? Okay, so really, the rho player should pick x to maximize its value. So now the rho player picks x star that maximizes or picks x that maximizes mean of j expected utility of xj. Again, j is between 1 and n. So what does this tell us? It tells us that we can write the following LP. We're going to say max of z, like we had before, such that I have a minimum of n things. So I'm going to say z is at most expected utility of x1. Z is at most expected utility of x2. I have n such inequalities. Notice that each of these is a linear equation in x. Okay, so I can write it out. That is a sum from I equals 1 to n of ui1 xi xi. And this is I equals 1 to n ui 2i xi, and so on and so forth, right? So all of these are linear equations. Here we have the implicit contribution, the implicit participation, but with coefficient 0, of the variables x1 to xm, right? Oh, this is m. That's m. And then we also need to make sure that x is a distribution. So x1 plus xm equals 1, and x1 up to xm is non-zero. And again, this gadget here is implementing as a set of linear equations this minimum over here. Right? So we have in this linear program, we're maximizing this quantity, and then when we do it is we maximize z such that this is the case. Now, whenever we write down a linear program, we need to worry about whether we really care about integer or fractional solutions. For example, that was the case when studying flows. In this case, we just don't care. Like if we get fractional solutions for x1 through xm, that's okay, because that's exactly what is a mixed strategy. So here there is no rounding considerations. So this is the LP for the row player. If you, for any particular game, you code this up and you stick it into some LP solver, the answer you will get is the x star. And the value that you get for the maximization problem is exactly the value of the game. Now, just so that you get used to this, I'm going to also do the same thing for the column player. So this will stick more. Because by the time this lecture is done, you will have seen this reasoning many times over. So we're going to do this same thing for the column player, and hopefully that will kind of clarify what are the analogies here. So if the column player plays y, which is y1 through yn, right? So there's only n strategies for the column player. Then the row player picks x to maximize now the expected utility on xy. So the payoff for, again, row, so we're always taking the perspective of the row player, is maximum over x, expectation of the utility over x and y, which is maximum over x of the sum over I equals 1 to m, u I y, xi. And like before, if we're trying to maximize a convex combination of numbers, it is best to just pick the largest number. So we're going to look at the max of I in M of the expected utility of I, y. Okay, it is best to put all the probability mass of x onto the I that gives the largest number here. So then column will pick y that minimizes the expression max I in M expected utility of I, y. Okay? So now we can write the analogous LP, which is in fact the dual, is minimum of W such that W is at least expected utility of IY, so 1y. W is at least the expected utility of 2y, and so on and so forth. I have m such equations. And each of these is a linear equation in the y's, right? Because this is sum from j equals 1 to n of u1j times yj. This, for example, is sum from equals 1 to n u2j yj, and so on and so forth. And then we also need to ensure that the yj's are a distribution by saying that the sum is 1 and they're all non-negative. Okay? And like before, all the variables are w and the yj's, which implicitly participate with a coefficient of 0 in the objective function. Okay? And this gadget here is implementing this max over here via linear functions and an auxiliary variable, the auxiliary variable w. And one can see that the coefficient matrices oh dear, this one doesn't write. The coefficient matrices in here are transposes of one another because the LPs are duals. Okay? So, and again, through strong duality, a deep fact that that Jelani mentioned in his lecture, but we haven't proved in this class and we're not going to. We know that the maximum value of this LP equals the minimum value of this LP because they're duals of one another. This value is the value of the game, and the X star that gives this value is the best strategy for the row player, and the Y star that gives this minimum value is the best strategy for the column player. So this is summarized in a theorem that is known as the minimax theorem. I'm going to write here. So the minimax theorem says that if you want to maximize over x the minimum over y of the expression expected utility of xy, then that is the same as minimizing over y the maximum over x of the expected utility over xy. And so this is the perspective of the row player's thinking, because he wants the best x such that given x, he's going to pay this. Why? Because the column player is going to pick the y that minimizes expression. And this is the column player's thinking. And the x that maximizes this expression, that's the x star, and the y that minimizes expression is the y star, and they have the same value through this theorem. That is a special case of strong duality. In fact, this minimax theorem was discovered and proved before a general theory of linear programs was developed by first, von Neumann and then John Nash. And actually the x star and y star are examples of what are called Nash equilibria, which exist in a more general class of games, not just zero-sum games. This mostly concludes what I wanted to say about zero-sum games today. So this is the only lecture about zero-sum games that we're going to have in this course. What I would like you to take away from this lecture is that is appreciate how, well, first and foremost, what is a zero-sum game? You have the general setup here. A zero-sum game is just a matrix of numbers, and you want to find X star and Y star that are the best strategies for either the row and column players. Now, given that this is the setup of a zero-sum game, what I want you to remember, first and foremost, appreciate how zero-sum games are a special case of linear programs by understanding how the strategic reasoning of either the row player in this case or the column player translates into a linear program. Through strong duality, these are the same values. And then you should be generally familiar with playing with concrete games, like cute little games like these, where you want to be able to sort of do this type of computations where you are either asked to find some optimal strategy or to understand what happens, if a particular player plays some strategy, maybe it's optimal, maybe it's not, and to be able to understand these things. Again, this is the only lecture on zero-sum games we're going to have. In the next lecture, we're going to talk about another example that is related to linear programming. So that's it for today.